In this video, we are going to derive integrated rate expression for second order reaction. In our last video, we have seen second order reaction with same reactant. Here, we are going to derive for different reactant. Second order reaction where the reactants are different. Two different reactions. Let us consider reaction, general reaction A reacts with B, gives product B. So how we can write the rate expression for this? R is equal to minus dCA by dt, or in simple you can write minus dA by dt, because here we are dealing with two different reactants, so it is better to write in a simple way, that is minus dA by dt minus dB by dt dP by dt. So here the concentration of product, right? So applying rate law, R becomes R is equal to K. So here it is the rate constant K2. Since it is a second order reaction, K2, the rate depends upon the concentration of reactant A as well as concentration of reactant B. So we know initially we have taken A moles of reactant A and B moles of reactant B. So at initially when time is equal to 0, no product is formed, therefore we can make it as X. After certain time, it forms X moles of the product. We can write here. I will just rub it here so that it is very easy to understand. I will write again. Maybe this also I will rub. So you know the reaction A plus B gives product, right? So let us first discuss what is the coefficient or moles. B, so initially it is Z. So this is at when time is equal to 0. After certain time, let us say time is equal to T, X mole of product form at that particular time. What is the mole or what is the concentration of B remaining can be determined by subtracting the product. So it is B minus X and A minus X. Now you write the rate law, or first you write the rate equation as I already told you, minus dA by dt minus dB by dt or dP by dt. So rate of the reaction becomes K2 into concentration of A, concentration of B. So since it is a second order reaction, it depends uh, upon the concentration of both the reactant A and B, right? So again I am writing A plus B gives product. We know the moles of the reactant A minus X, B minus X, and here it is X. Now it is easy to write the mathematical expression. So in terms of X we can write variables dx by dt is equal to K2 into concentration of A and concentration of B. We know the concentration of A. Concentration of A is what? A minus X, right? Concentration of B is what? B minus X. So this you substitute in this equation. how it will become? Dx by dt is equal to k2 into a minus x b minus x. Now you separate the variables dx by a minus x into b minus x. Then you bring dt into the right hand side so that it is easy for the integration. Now you can integrate. So integrate the equation dx by a minus x b minus x k2 into dt, right? So on integrating dx by a minus x into b minus b, it will be 1 by a minus b ln, so this is b, ln a minus x b minus x is equal to k2 into t plus the integration constant c. This you can remember. This is a mathematical derivation, no need here. So directly you can remember this. If you remember this one, then it is very easy to follow the next step. So from this equation we can find c. So to find c, we have to apply the condition t is equal to 0 and x is equal to 0, because at the time t is equal to 0 there will not be formation of product. The concentration of product will be 0 theoretically. So apply the value in the equation. So 1 minus a minus b ln a minus 0 b minus 0 is equal to k2 into 0 plus c. So how it will become? 1 minus a minus b will be there remaining, and ln a by b will be there c. So this is the value of c, right? So c is equal to c is equal to 1 by a minus b ln a by b. So substitute this c value in this equation. So it becomes 1 by a minus b. So I will just skip here so that it is easy. So 1 by a minus b ln a minus x. We have already this b minus x is equal to k2 into t plus, now you substitute the value of c here, 1 by a minus b ln a by b, right? This you can write like this also. Now you again separate so that it is easy. If you separate and simplify, the equation becomes 1 by a minus b. It is common, we are taking outside. Then ln b into a minus x, a into b minus x. So we are bringing this to this here and taking common 1 by a minus b outside, so that the expression becomes like this, equal to k2 into t. So t, we are going to find the value of rate constant k2, so that you can bring t also this side, 1 by t into 1 by a minus b in bracket ln b into a minus x and a into b minus x. So this is the rate constant expression for second order reaction, where the reactants are different means heteroreaction, heteromolecular, not same homomolecular, homonuclear or homomolecular, right? So once again I am just remembering A plus B gives product, where A and B are the two different reactant. Write the rate equation for that and then apply rate law to find the rate of the reaction. So here, since it is a second order reaction, it depends on both the concentration of both the reactant A and B, and find how much mole after certain time t reactant. uh, Integrate the equation. Here you have to remember the integration of dx by a minus x b minus x. Here, since mathematical derivation is not required here, that may lead to very long derivation. So directly you can remember 1 by a minus b ln a minus x by b minus x. Then find the c applying the condition t is equal to 0 and x equal to 0. Then you will get the value of c and substitute the value of c in the integrated equation. We can arrive the rate constant expression. K2 is equal to 1 by t 1 by a minus b into ln b into a minus x divided by a into b minus x. So this is the integrated expression for second order reaction with two different reactant. Thank you.